So the notes of my formal lectures, the PDF notes will be available. Okay, so first, maybe I thought I wanted to make some little tour of computer algebra systems that I like and that can be useful for research. And I generally recommend that everybody try out computer algebra systems. I think this is, sometimes I jokingly say, this is the chance for the young people to excel or to overtake older people, because old people, they had lots of time to generate all the wisdom. So they go to many lectures, they go to all the talks. So the old people, they know everything. And the young people, they're usually really good with computers. So sometimes the famous people make a conjecture and they haven't computed, they have only computed the examples they can compute on paper. And then somebody who can use a computer can compute the next example and find the counter example maybe. Okay, so let's take a quick tour of some computer algebra systems. And I will share some thoughts on them. Okay, so some people are joining the room. I can admit them as we go. So let's start with Sage, maybe. Okay, am I muted? Yeah. Okay, there was some echo, but I don't know. My computer is completely muted and volume, low volume. I think it's fine now. There's no. Okay. Yes, sure. Okay, so first of all, so many of you might know some of these. So the first I'm showing is this Sage Math. So this is a computer algebra system. And I'm also focusing on open source software. So let me say something about this. So there are some computer algebra systems that you pay for. Traditionally, this has been a model that people develop these software systems commercially. So the most known examples are maybe Mathematica and Maple. And these are, you have to buy a license, you have to buy the software and work with it. And so that's the financial part of it. But there's also a philosophical question about mathematics. If you do some computation and it is run in a closed source software, then you have no access to the source code. And by that, you have no access to see and at least in principle, check what the software actually does. While the systems I'm talking about are open source systems, meaning that the source code, all of the source code is available for you or the mathematical community in general to look at and check what the system actually does. So with the closed source system, irrespective of whether you pay for it or not, you have to rely on promises made by the developers about properties of the software. What does it do, and does it actually compute what it claims to compute, and what if there are errors? So in principle, with these open source systems, you could also fix them if you find bugs, and you often find bugs. If you do research with mathematical software, you often find bugs. Okay, so Sage is set out to be a replacement for Mathematica, so a throughout system for mathematical computation, and it integrates many other projects. So imagine you're trying to solve a problem that I was also mentioning today. You're doing something for all graphs. Say you want to solve the problem for each graph. You have a recipe how to make one of these A matrices, and from the A matrix you make the toric ideal. So now in an ideal world, on paper, you just write, I want to try all graphs on 5 vertices, all unlabeled graphs on 5 vertices. But then if you think about it, so what do you do? How do you make a for loop over all unlabeled graphs on 5 vertices? You know? How do you do it? So there is a book. So in the old days, you would go to the library. Go to the library, there's a book called the Graph Atlas. And in the Graph Atlas, there are all the graphs. 5 vertices starts on page 12 or so, I don't know. And so you go through this Graph Atlas and check all the graphs on 5 vertices. This is actually, when we get to the Markov basis database later, this is back in 2008, we did it like this. I think Sage was like maybe not around, or we didn't know about it. But of course, there's computer software. There's a library called Naughty that can enumerate graphs. So the cool thing about this Sage system is that it integrates all these different packages, a graph enumeration package, and then some general code with which you could make these matrices, and allows you to do something like this. You write a for loop. The language that's below it is the Python language, which probably many of you have heard is used all over the place in industry. All the machine learning libraries that Google is providing use Python. So you can in Sage, which is a dialect of Python, just write for G in unlabeled graphs on 5 vertices, and it will do the enumeration of these graphs in the background and run for you a for loop over these graphs. So that's Sage. So with all of these packages, there's always the problem, like, how do I install it? And it depends on the system, Windows, Linux, Mac, and so on. So I don't want to go into that too much. But yeah, Sage is like the all-around go-to thing that you can try. Okay, so then there's a new kit on the block, the OSCAR system. So that's German engineering. So OSCAR is the open source computer algebra research system. A system is not in the OSCAR, somehow it's open source computer algebra research. And it follows a similar approach. It's maybe not as encompassing over all of mathematics. It's more focused on the things we are also interested in, which is commutative and non-commutative algebra, computational discrete algebra. You can see like some of the keywords here. And it's written in a more modern language called Julia. It's a programming language. So when you interact with these different things, you're writing your code in the Julia language. Yeah, which is newer than Python and people like it. So, and then let's get to Macaulay 2. Macaulay 2. So Macaulay is the name of a mathematician who worked at the beginning of the 20th century, as probably many know. Has a bit old-fashioned homepage, but so there is a Macaulay 2 web. Can you see my, oh wait, why don't you see this updating? It stopped updating. Okay, I see something different than you. For you, it stopped when I started typing up there. Let me just try to share again. Let's see what happens. Nothing. Seeing nothing, hearing nothing. Participants can see your application, it says on my screen. Double click to enter full screen mode. No, this is not for me. This message is for the other computer. Oh, here we go. Okay, it's kind of slow, but my mouse pointer is over here. So there's a Macaulay 2 web where you can try this out in the browser. Of course, if you want to do more interesting things, you should install it on your computer to try it out. Okay, so I think this morning, Stefana used, no, this morning, yesterday, Stefana used the web interface of Macaulay 2. So I'm going to use this Macaulay 2 to, the updating is not great, to show you something, but I have, of course, have it installed on my computer. Okay, so let's try that then. Enough with the browser. How about this one? I don't know what I'm doing wrong. Is it just very slow? Or? Okay. Okay, that's certainly too small. So let's make text bigger. Make text bigger. Make text bigger. I don't know what's the. Okay, still too small. Maybe still too small. Okay, I'm giving away all. Okay, so the update is like really slow. What I'm doing here is it takes a while for to show up. Okay, so I'm starting Macaulay 2 by typing M2 on this command line. So now this greets me with yet another language. So one thing about this system is that you have to learn how to use them, but usually you get started by copying code from somebody else, and then you try to modify it, and then eventually you get used to it. So what's good about Macaulay 2 language is that it is very natural for us as mathematicians. For instance, if I want to define a ring R, that is a polynomial ring over the rational numbers, I just write what I would also write on the blackboard, and unfortunately it's not appearing. X1, X2, X3, let's see. Okay, here we go. I write R equals QQ. I write two Q's for this shadow Q. And then just the square brackets that we know from the definition of a polynomial ring. Let's say R is a polynomial ring in 4 variables. Note, this is a computer, and computers like computable fields. So I like the rational numbers a lot. Some people like finite fields, which have very fast arithmetic, but you're never going to work. I mean, there's some specific things you might want to do over the real numbers or over the complex numbers, but generally we do computer algebra with the rational numbers. And then you think about the Nullstellensatz, and you think, wait a minute, isn't there let K be algebraically closed assumption at the beginning of my textbook? And that's the case. So there's this second level where in our minds we have to take care of this problem. What's the passage from Q to C? And that, of course, becomes always relevant when we talk about factorization of polynomials and concepts that have to do with factorization. In my lecture on Thursday, which you will see streamed over Zoom from Karachi, I will talk about one such problem. Okay, so
is it possible to zoom in, like
further? Yes. I make it even bigger. So how is it now? Okay, it's zoomed out, but now it's downstairs here. Yeah? Okay, here we are here downstairs. A little better. Okay, so let's try to solve this problem of describing the kernel of this map. Q adjoint X1, X2, X3, X4 to Q adjoint ST. So this was in my first lecture, the example of a toric ideal where the rank of the kernel is not equal to the number of minimal generators. So I had this matrix 1, okay, what was it? 1, 5, 1, 4, 1, 2, 1, 1. So 1, 3 is missing. So this corresponds to the map that maps, well, X1 to ST to the 5, and so on, X4 to ST. So I'm going to define that map. The toric ideal is the kernel of that monomial map, and the computer algebra system will just tell me the kernel and confirm what I claimed in the lecture. So I need a second ring. Let's call it S. Is the polynomial ring over Q with variables S and T. Okay. Coming up. I'll start typing the map. Okay. So I type in S is the polynomial ring with coefficients in Q, ST, and it tells me, oh, I know S is a polynomial ring. Okay, so let's define a map. F is a map from R to S, and the notation is the other way around. You will see once it shows up. I will start typing in T to the 5, S times T to the 4th, S times T squared, S times T. Okay, what happened? Okay, you see, I've read map. Map has 3 arguments. First, the ring where I'm mapping. So in Macaulay 2, the arrows mostly go in this direction from right to left. Has to do with linear maps, by the way. So in algebra, have you ever wondered that when the maps in linear algebra, the maps go in this direction, but the matrix product is from the right. So that makes, when you have a map from Rm to Rn, it's an n times m matrix. So that's because the arrows are in the wrong direction. So in Macaulay 2, it's from R to S. And then I give, I define it automatically a K algebra homomorphism. So I only give the images of the generators. Yes, so this is the image of x1 is s t to the 5 and so on. Okay, so it knows the map now, and now I just type kernel of f, and once it updates, you will see a bunch of polynomials. So the computation was very quick, so I couldn't notice any computation time. I'm at 04. Input 4 is kernel of f. Oh, here we go. Okay, so you see 4 generators. And in this case, it's a homogeneous ideal, so the notion of minimal generators is really well defined. In the lecture, I had 2 degree 3 generators identified, and there's even a degree 2 generators. So those of you who know about free resolutions, I know we're only learning about them, but those who know will know that we can compute the Betti table of I. Oops, what did I do? Betti, what? Betti res of I? Betti res kernel of f. Okay, so there's the Betti table, and people who are experienced with this will know that this means that the second column means that there are 4 minimal generators, 1 in degree 2 and 3 in degree 3 necessary. Okay, so what else did we do? Okay, so then now I said that this is not the optimal way to do this. I said a better way to do this is to compute this saturation. Okay, so let's experiment with this situation. Of course, Macaulay 2 can compute such things, and it's just the colon idea. So let me briefly check what the 2 lattice generators were that I gave in the lecture, so that we're using exactly the same thing. Oh, I can just compute them. Oh yeah, let's start with this matrix. So let me show you how to input the matrix. A equals matrix, and now the matrix command gets a list of lists, and the lists are the rows of the matrix. So I'm gonna input the matrix like this. Lists in Macaulay 2 are done with the set parenthesis. That's a bit weird, but okay, it has to do with computer programming. There are lists and there are sequences, and okay, anyway, I'm using these. Am I using these? Yeah, probably. Okay, so here's my matrix, and it already knows that it's a matrix from, it does some sort of type inference, yeah? So it's a matrix from Z4 to Z2, linear map from Z4 to Z2. So I can compute the kernel of A, and it will give me these two. It's exactly the 2 generators that I had in the lecture. So now I should make binomials out of them. So let's say F1 is my first binomial. This I will do by hand. There's also an automatic way of doing this, but let's do it by hand to practice. So your practice is you check that I do the right thing. What do? I take the first column. The first column is 0, 1, minus 3, 2, and I make the corresponding binomial. So this is a vector m in z to the 4 corresponds to binomial. So what's the general form of the binomial? Quick check. Who wants to? Yeah, x. Sorry, only one. So you go first.
X power u minus lambda power 3.
X power u minus, yeah, but this exponent vector corresponds to a specific binomial. So
Plus minus
yeah.
x.
xm plus minus
Minus.
xm minus. So I decompose into positive part and negative part and take these two monomials. Okay, so this is the one corresponding to this. So I do this twice, once for the first column, once for the second column. Okay, so I started x2, and so I have to do what? What comes next? x4 squared. Excellent. So you will know that x3 cubed goes here. Homogeneous, and f2 is then x1 times x4 cubed minus x3 to the fourth. And now I take I prime to be the ideal generated by f1 and f2. And I think I didn't say, I'm also going to say I equal to kernel of f, so that we have the same notation. So now we have this ideal I and this ideal I prime. And I prime is a subset of I. So with Grübner basis, you can check all these ideal containments. So I can check this. That's true, yes? Oh, maybe they're equal? Let's check. Maybe I just got lucky and they're equal, but they're not equal. In fact, the toric ideal is actually bigger. And I claimed that you can do this saturation. So how do they do the saturation? So I can do a colon ideal in principle just with colon. So I can do x1 times x2 times x3 times x4. Let's see what happens. This is just one colon ideal. It's called I double prime. Is I double prime equal to I? No, not yet. It also only has 3 generators, and there's no quadratic generator. That looks suspicious. So let's try with I triple prime. I triple prime should be I double prime colon. Ah, there's a quadratic generator, and it's exactly 4 generators of the right degrees. Looks pretty good. So maybe I triple prime is equal to I. Yeah, there we go. Okay, there's also a saturate command, which does this in one go. Except I don't really remember the syntax of the saturate command. So let me have Macaulay 2 help me with saturate. And then it outputs lots of text. If I scroll up here, I hope you can do this. The better way, which I'm not doing here because I need to switch to the browser again. If you type, instead of help, you type view help, it opens this thing as a HTML version in the browser, which is usually what you want to do. Okay, saturate works like this. You call it with 2 ideals, I and J, or with 1 ideal, I. These are the 2 ways to call it. Let's see what this means. I is an ideal, a monomial ideal, or module. J is an ideal, a monomial ideal, a module, or a ring element. Okay, so this is probably the one we're looking for. I is an ideal, and J is a ring element. Generated, okay, if not present, if J is not present, then it takes the ideal generated by the variables of the ring. The ideal generated by all the variables is not what we want. We want the one product of all the variables. Yeah? The other one is very important for projective geometry. That's why it's the default thing. Okay, so let's try saturate I prime and x1 times x2 times x3 times x4. Oh, is that equal to I? Yes, it is. Yeah, so it iteratively runs this again and again. Okay, so that's one thing. So then I wanted to show you how to reconstruct the A matrix from the lattice generators. Okay, this is also something I claimed in the end of the Monday lecture. So let's see, we had kernel of A. We can work with this. I call it L. I call this the matrix L because it's already in the right format. So in the lecture, I said if you So what is it mathematically we're doing? We have some letters. Some letters L in Z to the N. And we want to find A such that L is equal to the kernel of A. And this letters here, so if you're starting with the toric ideal, e.g. read of L from generators of toric ideal, want to find A. I also claimed without proof that every toric ideal, every unital binomial prime ideal is of the form IA for some A. So let's find the A. How do we do it? We first construct this L by reading the exponents from the generators. Now we find this matrix with the Smith normal form. Okay, Smith normal form is built in. We are lucky. We type Smith normal form of L. Oh, that's a problem. Oh yeah, this is good exercise. So what happened? Let's read the error message. Something didn't work. Error. No method found for applying Smith normal form to the argument image of a matrix. So what happened? The data type is wrong. So this kernel of A is a module. It's a Z module. It's an abelian group. So it's not a matrix, and Smith normal form is supposed to be applied to a matrix, namely this matrix. But what I didn't observe is that this thing is described as the image of this matrix. So how do I get the matrix? I think I'm just going to try type matrix. Let's see if that works. Matrix of L. No. What? How do I do this? So a good thing that you can always do, you can look in the inside of objects here with the peek command. Let's find out what this thing is made of. Okay. Yeah. Gens L. Okay. Generators. Generator. Of course, generators. Sounds good. Generators. Gens is the short form for generators. Generators of L. Okay. Generators of L is the matrix that I'm looking for. Okay. So what were we doing? Smith normal form. Smith normal form of gens L. Okay, there we go. The Smith normal form. Who likes abstract algebra? So the Smith normal form is a really cool device. It allows you to, when you have an abelian group, finally generated abelian group, to compute the presentation, in terms of, what are you doing? Wait, it's an IT nightmare. You just allowed this device. Oh, LAN cable. Okay. All right. Thank you. You just connected USB device and click yes. Now all my data is gone. Okay. Okay. What was I saying? Abstract algebra. So if you have a finitely generated abelian group, there's the classification of finitely generated abelian groups, product of finite abelian groups with the free part. Yeah. And so the Smith normal form computes this. So this tells you this finitely generated abelian group is of the form, well, Z2 is the result. Okay. And so from the Smith normal form, the output is 3 matrices, which are the Smith normal form. So it writes L times S times T. ST are invertible. So they have determinant 1 or -1. Is diagonal. So diagonal. And so this is a sublattice of Z to the N, so it's automatically free. So the group, as a group, it must be isomorphic to Z to the K for some K, and the K is 2 in this case. So this is what we read from the 2 ones here. So the presentation that it's giving us, it's Z mod Z times Z mod Z times Z2. That's the presentation of a group. So this part is irrelevant. That's the ones here. The ones here tell me that it's Z mod Z. If there was a 2, it would be Z mod 2Z. Yeah. So this is a computation that can be done. Z mod Z is nothing. It's trivial. A Z mod 1Z. Yes. So this is what I read. I read from the diagonal that there's no torsion. If the diagonal was 2, 2, it would be 2Z, 2Z. There would be torsion. Okay. But it's a theorem that with historic ideals, these lattices have no torsion. It's a theorem of Eisenbart and Stoff. It's part of the characterization of binomial prime ideals that I didn't fully explain. We just take it as a theorem. So the second is the matrix S, which is multiplied from the left. The third is the matrix T, which is multiplied from the right. Remember, multiplying from the right does column operations, multiplying from the left does row operations. So after doing row operations to L and then column operations to the result, you get this matrix. That means, so in particular, this implies that SL is also of the form something and then zeros. And by what you know about matrix product, this means that the lower part of S times this L matrix is 0. And now you do the dimension, what is it called? The rank nullity theorem over the integers to see that you need to take as many rows as you have 0 rows here from your S. Okay, and what happened? Aha, something interesting happened. So this time, so it tells me I take the lower 2 rows here, and they are equivalent, but they're not the same. You see, it's subtracted. First of all, the all ones row is the bottom row now, and also subtracted the row ones. Yes. So if I add the bottom row to the top row, I get my original matrix back. But it gave me an equivalent matrix. Okay. This is how I can find an A matrix to a given lattice. Any questions about this?
Can you repeat how you pick out the rows? How do you see the equivalent matrix for which rows? In this case, it's obvious because you can see it.
How many rows I should take?
You know how many rows you should?
Yeah.
Yeah.
How many rows? I mean, how many rows is just disregard the top diagonal part and take just the lower part of this equation. And the T matrix does column operations. Column operations on the lower part are irrelevant. Yeah. So you take, so the number of rows of A can be computed from its n minus the rank of the lattice. It's a bit unfortunate that both are 2, that the rank of A and the rank of the lattice are both 2 in this case, but certainly 4 minus 2 equals 2. Okay, so now this is really small matrices. So now I have to switch back to the browser, I think. But now I'm connected to the cable, so maybe that's easier now. Okay, so let me introduce you to this where we were before. Let me introduce you to the Markov basis database. Please. You see, it's the third tab. Let's click on the third tab. Here we go. Okay, so let's go to the home page, start. Okay, maybe it takes a while for the home page to load. So this is this website, markovbasis.de, and it has, if you see in the top left, it has 298 entries. And maybe this is a good example already, because we see many so-called graphical models. Are you going to say what a graphical model is tomorrow? Maybe. So this is all discrete. I think Carlos is talking mostly about the case of normal distributions. So this Markov basis, this whole business is all for random variables that take finitely many states only. Yeah? So let me explain how to construct one of these A matrices for a graphical model. So if G is a graph, unlabeled, undirected, well, labeled, undirected. In this case, so there's no causality or something, undirected on n vertices. So then we form the cliques. Which are the complete induced subgraphs. So now this says binary, the connection has timed out. Okay, so this is about tables that, so the linear map A maps R, Z, N. I've been using N. N to the 2 to the N. So this is binary. Binary graphical model. So xi takes values 0, 1 for each I. So the probability tensor is P0, 0, 0 to P1, 1, 1. So there are 2 to the n such strings. And I make a big table, a big space, which accommodates, which has one dimension for each of these choices of strings. And then it maps to the marginals for these cliques for the complete subgraph. So I do a direct sum for f clique, and I do a z z to the 2 to the size f, and the map takes yeah, maximal clicks. Yes. It simplifies the matrix, but it doesn't change the result. Including all the other clicks includes many dependent rows on the matrix. So it won't change it. Okay, so now how do we say this? So we do U sub x. X is in 0, 1 to the n, maps to the vector U xf plus xf plus indexed over f in these cliques. Okay, and I think the best thing to do is an example that is not the example that was in the independence model, but the next more complicated one. So e.g., you have this graph, 1, 2, no, this is bad. I need to take a 4 cycle because a 3 cycle is a click, and then everything is boring. Okay, so let's take the 4 cycle. It has, the clicks are just the edges. Yes, there are no complete graph on 3 vertices, a triangle, there are no triangles, so the clicks are the edges. So here I will have n equals 4, and I have my map A. It takes u, x1, x2, x3, x4, and maps it to. Okay, what are the edges? It maps it to u, x1, x plus x4, and that's itself a vector. Yes, that's a vector in this case of length 4, because x1 and x4 can be 0, 0, 0, 1, 1, 0, 0, 0, 1, 1. Okay, then the next one is 1, let's say 1, 2, u x1, x2 plus u plus x2, x3 plus, and u plus x3, x4. So that's a vector of length 4 plus 4 plus 4 plus 4 is 16. And that's a vector of length also 16, because 2 to the 4 is 16. Okay, in this case, it's not the format is quadratic, which is rare, but this happens. So let's now find this. If I can connect to the internet, I'm going to find this thing in the Markov basis database and see what's going on with the Markov basis. Okay, on my computer, I'm back on the Markov basis database. So I know what to look for. I'm looking for no three-way. Oh no, I'm looking for cycle. Sorry. Or cycle. Okay. It will be coming. Okay, this is not the one I was looking for. I found some entry using the search function, but not the one I was looking for. Here, it's right on the front page. Okay, if you could see the front page. Except that is what to do while you're waiting. I found it, but it's loading. I can start to explain what these things mean. So these things have a name. So each row, okay, here we go. Each row has a name, some cryptic name that we chose for it. And the one I'm looking at now is C4, cycle of size 4, bin for binary. And then there are some columns here. So this is the number of random variables is 4. Some number is 8. I forgot what it is. Some number is 16. And then a bunch of green check marks, which are properties that this thing has. Generating degree seems to be 4. And there are 16 elements in the Markov basis. And it's the binary graphical model of C4, which is what I claimed. The binary, it's also the binary matrix model of rank 2 and added columns. So sometimes the same matrix arises in different ways. So if I click on it, I find a bunch of files, and one of it is the model description. Oh, some things make me sad. Okay, let's try something. In this browser, open a text. Okay, so the browser won't open this text file because it's called .mod. So I will show you again on the terminal. So this is a file that describes the model. So it's called the mod file. I downloaded it from the Markov basis database. It says we have 4 variables. The sizes are 2, 2, 2, 2, and here come 4 marginals. A marginal one marginal is 1 click. You should compute the marginal for is 1, 2. 1 is 2, 3. 1 is 3, 4. 1 is 4, 1. So we'll be in a bit different order. So the order will be 1, 2, 2, 3, 3, 4, 4, 1. So the matrix that we get now will be commuted, but doesn't change much. So 42 comes with this program gen model, generate model, which generates this matrix C4 bin, which generates the A matrix. And now we can see the 8 matrix in all its beauty, C4 bin dot mat. And as I computed, it's a 16 by 16 matrix that looks like this. Here you go. And so the thing that, how this database was created was to go through the atlas of graphs. Back then we used the atlas of graphs, which is this thick book which contains all graphs, and create these model files, and then from there it runs automatically, because the next command would be Markov C4 bin. Okay, I'm typing Markov C4 bin, and then there's a cool output, which you can see soon. So I'm using 42 now, which is this command line program. Yeah, so gen model and Markov, the things I'm using are part of 42. The computation is already done. It took 0 seconds. Yeah.
Wow. Because I would have searched for the graph. So there's a search function on the website.
So the search function on the website, you can use keywords. It will just search through all the strings that are associated with the models where this keyword appears. So I typed cycle into that, and no, I don't know what I typed into it. So I got this other thing. And then I just noticed, after going back to the front page, I noticed that the 4 cycles were among the first models that were coming, and the one I was looking for was on page 2. Okay, so now something happened, yeah? So now there's a different 16 by 16 matrix. By sheer coincidence, one of the 16s is no coincidence. One of the 16s is this end. The second 16, the number of columns is this n. Each row is one element of the Markov basis. And what the 16 that is coincidence is the number of rows. Is there, by coincidence, there are 16 Markov basis elements. Each row is one of these integer vectors, and there you go. So now my quiz question is, what's the Betti table? What's the first column of the Betti table? How many generators in which degree do we have? Or what's the highest degree? I mean, we're bad at counting. What's the highest degree that appears in this Markov basis as a minimal generator? This is a general phenomenon. The computers are so good, it takes 0 seconds to compute the result that you want, and then it takes very long to understand what you have computed. It's a general phenomenon. It happens to me also. It's like I was in the same situation. I computed a Markov basis, and Bernd Stumpf was very excited. What is the degree? What's the maximum generating degree? And I was standing there. 16 years ago. It's another 16. Okay. So these we read it from the number of positive entries and the number of negative entries in the rows. Yes. So this is a vector. These are one row is one of these M vectors. You could decompose it into positive part and negative part. by coincidence or by properties of this model, there are no twos whatsoever. It's only +1s and -1s. This is a research problem. Why are there only +1s and -1s? Why are the generators square free? Does it happen for every graph? Yeah, this is a good research problem. It's known the answer, but anyway, 16 years ago it was a good problem. So so let's take the bottom one. It says like there's one, a +1, there's a +1, there's a +1, there's a +1. So that's degree 4 already. Yeah, and that's the highest degree that appears. There are also some quadratic generators. For instance, the first row is a quadratic generator. Okay, and so maybe to wrap up, let's switch back to the one more time to the database and look at some of the really big examples that have been computed with 42. Or the properties that we looked at. I think mostly this, many people have been focusing on the degree in which it's generated. So for instance, there's this very nice, I find very nice result that if the graph is K4 minor 3, which is a property you might know is the graphs of tree width 2, if you have studied graph theory, is the ones that arise from the series parallel construction, then it's generated in degree 4. That's a cool result, I think. Okay, what is one of the bigger models here? So let's see. So we did this, the C4. If you look here where my mouse pointer is. So now you can do this experiment of letting the indices grow. So now the largest one we have here is 3 random variables of sizes 3, 3, 3, 3. So then this becomes a 3 to the 4. And this becomes something you can compute. And then it's generated in degree 6. So the result I was mentioning was for the binary one. And there are 31,914 elements in this Markov basis. But here you see if you do 2, 2, 5, 5, you already go to degree 10. And there is this universality result. If you let 2 adjacent ones grow, this degree will be unbounded. Yeah, this has been understood by now also. But what I want to point out is that this whole Markov basis research, all these theorems that now seem like very nice theorems, graph theoretic properties connected to algebraic properties, they are really grounded on experimentation. And the experimentation was done by this program 42, which was specifically developed for like one curious problem that, I mean, it's probably safe to say that Emmy Noether wouldn't care at all about. You know, computing the explicit generators of some ideas, not something that was interesting in the abstract algebraic theory. Okay, and now we do it, and this is my impression of what mathematical research data is and what it is good for. And so I'm a big fan of combinatorial databases, so let's make more of them. Okay, I'll stop here.
Is there any question?
So, Thomas, at those minimum working basis, there's like minimum size.
So the unique, they're not unique. We had one, there's one column which says unique. So you can test this uniqueness property by going through all the fibers that you need to connect and check if there are 2-element fibers. But the degrees that appear and how many are unique because they're Betti numbers. These are all of these ideals are homogeneous. Yeah. So everything that comes from graphical models is always homogeneous. So it's all well defined, and these are all minimal Markov bases.
Okay, if there is no question, so let's answer. let's meet tomorrow at 9:30 for the next. meeting.